It is my real pleasure to introduce Erika Sturm. Erika is a Womanium Quantum Solutions Launchpad Fellow. She has been with us for a year after last year's program, where she works partnering with the Naval Nuclear Lab on DFT simulations for NV centers in Diamond. Erika's background is both in chemistry and applied mathematics. She did a double major at the University of Miami and then continued graduate school at the University of Chicago, where she developed, and now I need to take a deep breath, she developed a fragmentation approach using reduced density matrices to improve the energy calculations of small electronically correlated molecules. So if you have questions about that later, please let her know. She also worked in the areas of theoretical condensed matter physics, in machine learning, and now, as a Womanium Quantum Solutions Launchpad Fellow, investigates spin dynamics of nitrogen vacancy centers in collaboration with the Naval Nuclear Lab. And we will first show a video from QBronze, because he didn't make the entire part of his lecture on Wednesday. So we will add that part for like 12 to 14 minutes, and then we will dive into a very exciting lecture by Erika. Erika, can you introduce the topic of today's lecture?
Yes, today we will be discussing Grover's search algorithm. You've heard a little about it today from Dr. Oliver, and I will be continuing that. This is part of the QBronze lecture material, so stay tuned.
Yeah. And one topic that is useful for that is phase kickback.
We'll start building towards this foundational steps for quantum algorithms. And the first step towards building quantum algorithms is to make sure that we can do everything that you can do quantum in a classical computation. And the first time you hear that, I'll repeat that. We want to ensure that you can do everything in quantum computation that you can do in classical computation. That perhaps might seem obvious if you haven't thought about it first, because you're like, hey, isn't quantum computation a superset of classical computing? Yes, it is indeed. But then there are subtleties. In what way? Well, quantum mechanically, we've identified the fact that all transformations, i.e. evolutions over time, are going to be unitary or reversible operations. Classically, we don't necessarily have that restriction when we think about applying logical operations. Case in point, think about how in a standard kind of logical circuit, you think about applying the AND gate. So that we are forming the building blocks of how we want to think about quantum algorithms and quantum circuits. We've seen some almost toy examples, if you want to call quantum teleportation a toy example, but we want to be able to now talk about general algorithms, hopefully by tomorrow. And towards doing that, we want to be able to say, hey, how do I do anything that I can do in a classical circuit? The first thing that we have got to overcome is this notion that all quantum transformations are reversible. But when I apply an AND gate in a standard representation in a classical circuit, it's not a reversible transformation, right? If I know the value of this AND gate, I can't reconstruct what the input values were. If AND is 1, then yes, I know both the bits were 1, 1 input bits. But if AND is 0, then I don't know which of the 3 input possibilities occurred. How do I overcome that? Well, I could potentially add another output bit in my classical bit, but then what value should this take? I do want the AND value itself. Should this be the X value or should this be the Y value? I still miss a bit of information. And so one standard representation of thinking about this, and this is now completely classical, right? So classically, we can also implement all logical transformations in a reversible manner. I'm not an expert in the history, but from what the brief reading I've done is that when the initial digital logic and circuit design were being developed, part of the proposals were in fact to implement all transformations in a reversible manner. You can kind of see the benefit of that as well, because it's a reversible transformation. You're kind of, in principle, implementing it in a without any loss of information fashion. So the nice kind of outcome, or well, nice in a way, in a bad way. The reason why your laptop on your lap today, on the phone that you're holding, or the device that you're computing on is heating up, because all the circuitry is performing computation in this irreversible way. Information is coming in, some of that information is lost in the output. Where is that information going? Well, part of that is the heat that comes out of your computational device. And if you implement it in that reversible fashion, then at least that information is not getting lost. So since all transformations in the quantum case need to be reversible, we have the structure that will impose that any classical computation that you have, if were thinking about it in this way, we will now think about it in this way, where you have all your original input preserved in the output, hence your transformation is reversible, and you have an additional amount of memory, depending on whatever is the amount of storage you need for your output, that will actually start and be initialized, let's say in the 0 state or a known state. And you will have the value of the function you wanted to compute, whatever logical gate you wanted to have over here. In this simple example, it's the AND gate. It could have been something else as well. That additional value of the function will be computed into this additional storage. Hence, in this way, it's easy to convince yourself you can apply any function, or you can implement any logical circuit in a reversible manner. And so this is the way we'll think about classical gates implement as unitaries. So the idea is this A perhaps is not just a single qubit, it's a sequence, it's n qubits combined together in some state A. This B is your additional bit. And let's think this, this unitary gate, B sub f, is the encoding as a unitary of this Boolean function f that maps n bits to a single bit. So these A then represents the input in terms of n qubits, encoded in n qubits. This B is the single additional bit. And after implementation of B sub f, you will have the function f evaluated on the input A, XORed into whatever was the value B. And you can easily convince yourself that this is going to be reversible, because if you just imagine applying another B sub f over here, well, you'll just have another parity of f of A come in over here. Well, f of A parity f of A will equal 0. And so you'll get exactly what you started out with in the output case as well, in the additional bit, which will be just B. So this is our standard dictionary for applying any classical gate, that you have this additional memory, additional storage, and you will XOR your result into it. For many of our quantum algorithms, we'll think of them as an oracle. We don't always have to think of it as an oracle, but here in many quantum algorithms, we'll think of it as an oracle that's implementing some function f. All right. Using this representation, we'll implement a nice trick called phase kickback, which is really just a little bit of playing around with the math of what we just defined. So here, when I gave this representation to you, we kind of didn't think about the superposition, right? What is the parity? Parity is just the XOR logical function. So if you've got A and, well, A and B is not a nice choice on this page. Let's choose X and Y. If you've got X and Y, then parity of XY is just 1 when exactly one of the input bits is 1, right? Or in other words, it's counting even or odd number of ones on the input. So in these two cases, I value it to 1. In the other two cases, I value it to 0. Right, so that's the logical XOR parity. Okay, so what's the phase kickback trick? Note that in the previous example or definition, we had fixed B to be, let's say, some value 0 or 1. But now when you're talking about quantum information, this state doesn't necessarily need to be in 0 or 1 state. I could choose to define it to be in some other state. In this specific case for phase kickback, I define it to be, let's say, in the minus state. And that's easily doable, right? So you start, if this was initially B, B was equal to 0, you just apply first the X gate to make it 1, then you apply Hadamard to make it the minus state. And so you can easily get the minus state being fed in over here. Well, how will this B sub f work out based on this definition? It follows similarly by definition that, well, B sub f applied to A minus, well, let's expand out the minus thing. It becomes this. Let's just apply bilinearity. B sub f of A tends to 0, B sub of A tends to 1. In these two cases, I can apply directly the definition over here. So here it will be 0 parity f of A, the 0 from here. A was the input, so f of A. Same over here, 1 parity f of A. So you get this longer expression. So far, the way we've been doing it, it seems like pretty much by definition that the output is being computed into this additional storage bit. The phase kickback is a nice trick where we now observe that, well, if f of A is 0, So I'm just doing conditional reasoning. If this f of A was 0, then this expression over here simplifies to exactly this, right? So imagine that A has been taken out as a common factor. F of A is 0, so this will be 0 parity 0. So this simplifies to 0. 1 parity 0 will be 1. So you'll get 0 minus 1 as the value of this qubit over here. Whereas if f of A was equal to 1, so you'll get 1 parity 0, 1, 1 parity 1, which is equal to 0 over here. So you get 1 minus 0 as the state of this additional storage qubit, conditioned on the fact that f of A was equal to 1. These two equations then can be concisely summed together, or represented together via this. So you just note that essentially you have to just control this minus sign based on the value of f of A and just multiply it out with 0 minus 1. You can do your calculation backwards to verify that indeed this is the case. F of A equals 0, minus 1 to the 0. So that's plus 1. You get 0 minus 1 back, minus 1 to the 1. You get a minus 1 sign out. So you get 1 minus 0. So that works out. So what happened now? This computation over here, where we had defined F to be computed and being stored into this additional storage for the purpose of implementing the circuit in a reversible manner, has now found its way back by basically saying, in the sense that this additional storage, you now note, is actually exactly in the state that it started out with. And the value f of A of the function that I wanted to compute, the actual value that I wanted to compute, has been stored in the phase of the state, not in the state itself, but rather the sign in front of it actually has the information about f of A. And that's cool. So now, because the reason being, now you can take this additional storage and kind of throw it away. It's no longer needed because your computation still, your value is in the phase over here. And here's kind of the key big picture intuition about how many of quantum algorithms work. This has already happened. And if you expand out the computations of the teleportation protocol about the superdense coding protocol, that quantum algorithms work by utilizing the fact that rather than the convex combination of probability vectors that we had for classical randomized information, in quantum information, you had these vectors now summed up via amplitudes. These amplitudes could potentially have negative signs in front of them. And just like we recall from high school physics, that waves have constructive interference and destructive interference. That's exactly what's going to happen over here. You get you get amplitudes over here where the signs will get flipped in terms of positive or negative. And the goal of quantum computing is to figure out, or quantum algorithm is to figure out a unitary that allows you to perform constructive interference for the specific states that correspond to the right answer, and destructive interference correspondingly for states that give you the wrong answer. And hence, you are amplifying essentially the probability with which you'll get the right answer. If you can amplify the amplitude exactly such that the probability value is to 1, you've got a zero error algorithm. If you can amplify it high enough, you get an algorithm that works with high probability, and so on and so forth. And that all kind of is already kind of evident over here from the phase kickback trick, where you note that the information that I wanted to compute has been stored in the sign in front of the state. All right. So this definition that I had in over this slide over here, where the information is being stored in this additional storage, via the phase kickback trick, that same information is now showing up over here in the phase. And that's something that will be used in multiple quantum algorithms.
And as QBronze said, that is something that will be used in a variety of algorithms, and that includes Grover's algorithm, which Erica will explain shortly. First though, Erica, people are intrigued because you were a Womanium participant last year and now are also following along, but now you lecture here and are doing research. Can you briefly share about your Womanium trajectory?
Yeah, I actually joined 2 weeks into the program. I missed QBronze. Fortunately, some of you may already be aware, and from your very kind introduction, I have a background in quantum mechanics and chemistry. So I was able to catch up that first material very quickly. And I enjoyed the program a great deal. Was very active in Discord. Some of you are aware of that right now. I live my entire life in Discord, not just for Womanium. That's where my friends live. So I was fortunate enough to be selected for a QSL, a Quantum Solutions Launchpad, which is a program run through here. I'm sure there's been discussion about it and there will be more. And for the last, let's say, 10 months, I have been working in collaboration with the Nuclear Naval Laboratory. I believe they are giving a talk in a couple of weeks, but we've been working on the Nitrogen Vacancy Center in Diamond and the quantum computing, quantum sensing world around that modality. And then last month, you reached out to me and said, hey, want to do this? And I said, absolutely. So that's the 30-second, well, I guess not 30 seconds. That's the minute-long version.
Amazing. Very exciting and really inspiring for everyone, because it means all of you are here in the program now, you will learn a great deal, and it can open up opportunities for you to join research, to become a teacher yourself. Maybe you can start at small scale, teaching at your own university or high school or to your peers. Spread the word of quantum, improve your own skills, and climb that ladder. Today's session might go over a bit. We prefer to explain things well than to rush it through. So take your time, Erica, and we will make this whole recording available for everyone who is now, who says on Discord, oh, I'm quite lost after these QBronze lectures in the first week. It is very difficult as a new topic, and take your time to learn it. It is a lot of content in 1 week. Take your time to study it, do the exercises. I can't emphasize that more, because with that hands-on experience and going through yourself, from that you will learn so much, and the Discord server will be open to ask your questions and discuss together. Erica, please start sharing your screen, and then we will get the lecture started on Grover's algorithm.
I want to just have a little PSA out there before I share my screen. That is absolutely true. This stuff is difficult. If you could understand it on your first attempt or your first week, you wouldn't need a class. And that's true for everything, right? We are not designed to learn everything all at once. That's not the way humans learn. There are some people out there, they are amazing, but they are the minority by like a vast number. It's okay that you don't get this. It is brain breaking. It doesn't behave like classical reality. That's the point. It's quantum. It's not like anything you've ever seen before. So with that, let's go look at something new. So for the record, I will be trying to keep an eye on the Discord chat as we're going through this. So if I catch your question, I will try to answer it. If I don't, I'm sorry in advance, but hopefully some of your classmates can help. And over time, I will be asking some questions as we go. So feel free to shout out an answer or not, no pressure. And here we go. Okay, so today we're going to discuss Grover's algorithm. And this is part of your QBronze lecture material. So just a really quick overview, we're going to start with a math review. So this is going to include things like symbols. What is phase kickback? What is an oracle? And then we're going to discuss what is the problem we are trying to solve. The unsorted search problem. We're going to define that and give a couple of very basic ideas about what that is. And then we're going to discuss Grover's algorithm. Now, there are several ways to understand this algorithm. We are going to present depending on how you want to count, between 2 and 4, because there are 2 like very math heavy ways, and then there are 2 visualization that have very little to, there's like a picture that you can associate with each of the algorithms. So, 2 to 4 ways to think about it. And the first would be the inversion about the mean, and the other one is phase rotation. I want to emphasize now, and I will say this again later, this is the same algorithm, it's just different ways to think about it. And then we'll conclude with some final thoughts. Okay. So first a review, I said we were going to do some math stuff. So you guys have been working with Gibran. I realize I'm a completely different lecturer, so I want to make sure that we all have a consistent way to talk about symbols and that my notation is familiar to you. And if you are watching this later on, you can always come back to this. If you're like, I forget what that symbol is, come back here. There's a reason I wrote it up. So the very first thing, oops, getting a little excited there. A ket is a column vector. This is many rows, one column, okay? The X is a string. It could be a single qubit, it could be many. So a single qubit or bit would be 0 or 1, or it could be an entire string like X equals 101. And when we stick it in a cat like this, I mean the vector that represents this value or this string. That's what this means. It's got a best friend. Its friend is a bracket, like bracket, right? A bra is a row vector. Many columns, but only one row. It is the conjugate transpose, which means you flip it on its side, and if there were imaginary numbers, you take the conjugate. If it's real numbers, okay, that's just a transpose, okay? This is the symbol we use. That is a dagger symbol. That means take the conjugate transpose. I use the words operator and matrix interchangeably, so if I say one and you're like, wait a minute, I thought you meant something. Nope, same word. It's because we represent operators as matrices. So I use these words interchangeably. Don't be afraid of that. Okay, when I show, if I show quantum circuits, and we're not going to do a ton of circuit diagrams here. That's kind of a little too in the weeds for today. But when I do show them, I'm going to be using little endian notation, which is to say that the least significant bit, like the ones place, that's going to be at the top. And when you write it out, as a number, it will be the rightmost digit, the ones place. This is similar to Kiskett's notation. There are several others that use this notation as well. I know Circ does not. Circ is the opposite. It is big endian. But here we are going to use little. So math review continued. This is a tensor product. Hopefully you've seen that before. This symbol is the Boolean logic symbol. So if you've done any classical computing, this might look familiar. It works the same way here. This is exclusive OR of A and B, which is to say only one of these can be true at a time, not both. If A is true and B is true, the overall exclusive OR is false. Okay. Another way to think about this that sometimes is useful is that if you say that A is a single bit of information, or qubit, and you take one XOR A, that is modulo 2 addition. So you add them together and you divide by 2 and find out what the remainder is. Assuming that A is a single qubit. If it's more than that, if it's a whole string, it doesn't work this way. Okay. Okay, just checking in the chat. So there's a common shorthand because nobody, at the end of the day, humans are lazy and we don't want to write things out forever. So we come up with shorthands. So there are several ways to write equal superpositions for n-bit strings. I've displayed a few of them here. So if we have the Hadamard gate with a tensor n, this means we have multiple Hadamard gates across multiple bits or qubits, excuse me. So in this case, it would be the, because this started as a, can someone please tell me if you can see my cursor on the screen? I need to make sure that if I'm pointing at something, you know what I'm doing.
Yes, we can see your cursor.
Thank you, everybody. Okay. So, oh goodness. Yes, everybody, God and everybody has said yes. So that's a good sign. So this is the superposition of a bunch of zeros. This is not particularly exciting. And when I apply a tensored Hadamard to it, I'm going to get a bunch of pluses that are tensored together. Okay. We also don't want to write out all these zeros. That gets boring too. So we sometimes just write it like this. Now you might say, Erica, wait, why is this not with a tensor product and this one is? That's laziness. That's all that is. This is not 0 to the nth power because it's in a ket. Okay. At the end of the day, people don't want to write stuff or type stuff. So we use these shorthands. This is an equal superposition. This is the number, sorry, if little n is the number of bits or qubits, then big N is the number of possible options that can make. Okay. So take a look at this. I'm going to shut up for about 5 seconds, just let you read that. This is very common. We will use this a lot. Okay, oh, I even gave a definition. So here's an example with only 2 qubits, just to show you the way the notation works, okay? Nothing too outlandish. Hopefully you've seen this before. There are 3 different ways that we represent this. If you need to take a screenshot of what I'm about to show you, do it. If I try to use, we use all 3 of these. Depending on the context, one might be an easier notation than another. So what you might want to do, what I try to do is I try to say, hey, we're using this version or that version. I will try to point them out as I go. But these 3 things are equivalent in this little language here. This might not be somebody else's convention. Somebody else might not use like using little h. Okay, this is the notation I'm using here. So these 3 are interchangeable. Okay, I've hammered that enough. Let's talk about phase kickback. Now, I know many of you just saw this for the very first time, so this might feel very rushed, but you still have access to QBronze lecture that Marlou showed before my talk, and you will have this too. So if this is like, oh man, I don't get it, that's okay. It's new. This is a quantum mechanical technique that uses that kicks back the phase of one qubit to another one using a controlled operation like a C0 gate, and I've given 2 names for it there. C0 and CX are the same thing. So here we have a quantum circuit, just 2 qubits, okay? And I will be suppressing normalization coefficients for this because I don't really care about that right now. It's just the root of 2 anyway, or 1 over the root of 2. So that just clutters up the slide. So at this first stage, that's what we got. Nothing too exciting. I'm going to apply a NOT gate to the second qubit, Q1. And that means it flips, right? It goes from 0 to 1. Cool. Now we're going to apply Hadamard's to both. So we put both gates in superposition, and I've given 2 different notations for it. Now you might say, Erica, why didn't you break up the minus sign qubit? That's because that one's not going to do anything exciting, and I want to focus on the blue qubit, the top one, okay, or the least significant bit. Here's a C0 gate. So this should not, so if you're still getting used to the notation and the symbols, you know, just take a look. I'll be quiet for a minute, let you process. Notice the behavior of the blue bit, the Q0. That's the exciting one. Notice the red one didn't change. Red one's just going along for the ride. The blue one, though, the blue one changed between the third and fourth dashed lines. That's phase kickback because the phase from Q1, which is a negative phase, also now exists with that first qubit. Okay, that's phase kickback. And if you don't know how that worked, this is the secret sauce. This is what makes this possible. I strongly encourage everyone to sit down and work through this math on their own. It should take you maybe 10 minutes, not right now, but this is a very good exercise to work through on your own because A, it's pretty gentle. You only need 2 qubits and there's only a tiny bit of superposition. And B, this is kind of like the first exposure of like, hey, something's not classical here. This is weird. It's one of the quantum mechanical superpowers and we're going to use it a lot. Okay. So another thing that
can you repeat that one sentence you said, how phase kickback works? Can you repeat that once more per request by several?
Yes. So let me see if this answers the question. It's phase kickback is taking the phase from one qubit, qubit 1, the red one. We're going to take the phase from the red qubit and using the controlled NOT operation, we are going to kick it back to the first qubit, which is the blue one. We take the phase from the red qubit and kick it back to the blue one. So now they're both negative. I'm going to check the, it's not extracting information like an ancilla. These are both involved qubits. Although I guess you could use it as, well. No, it doesn't change the phase together. Notice that the red one never changes. I mean, yes, it changes when I apply the Hadamard, but notice that between here and here, the red one doesn't change. The red one just hangs out. But it does affect the other one. The red one doesn't change, but it does change the blue one. I wanted the phase of a qubit. The phase of a qubit, that is a fascinating question because it doesn't have a classical analog. So you are familiar with waves, you know, but you can also say, let's flip that wave upside down, right? Or what if you just shift it, right? Think of sine and cosine, right? We've all seen sine and cosine in your trig class. They're out of phase, aren't they? Right? But you can also think of it if they overlap and you were to add them up, you would get potentially areas that are much higher than any one in particular or much lower. Or maybe they'll cancel out in some places, right? So phases are a thing that we have in quantum mechanics that is fundamentally not a classical component. Just like a qubit has a value, it's 0 or it's 1 or a superposition, but when we measure it, it's a 0 or 1. The phase doesn't show up in measurement, but we can use the phase to do stuff kind of behind the scenes in a quantum mechanical fashion like this. Because so one of the superpowers here is that when I measure the Q0 state in when I measure this qubit here, when it's a plus sign, what result am I going to get? Right? Oh boy, we are getting in the weeds. Okay, in the engine. Okay, a lot of things happening in chat. Okay. We are not going to spend all day on this, but it is important to realize that the red qubit, the phase of the red qubit is kicked back or affects the blue qubit. That's the important takeaway here. The red one is influencing the blue one because there is a controlled gate in between them that connects them. Do you see that? That's the important takeaway here. I really do encourage you to work through this mathematics on your own when you have a minute, maybe sometime this weekend when you're chilling out. But we do have to move with a little bit of purpose. So if you at least understand that the phase of one interacts with the phase of the other, that's good enough. Okay. So one of the tricks that that we use this for is that it gives us a way to store information in the phase as opposed to the value. The value would be like, is it 0? Is it 1? Is it a plus state? Is it a minus state? But storing it in the phase means we're not affecting the value, we are affecting a different part of the qubit's property, right? Qubits have values and phases. Phase kickback allows us to move information from the value to the phase. And that's represented here. This is something that QBronze showed in his lecture a minute ago. We're going to go back through it again quickly. Again, I am suppressing normalization coefficients. Here we have a register A. It might be only a single qubit. It might be a whole mess of things, right? It might be a whole bunch of stuff. We're just going to call it A. And we also have this other qubit, and that's just one qubit by itself. And it is in the minus state. Okay. And then we're going to put it through this machine that I'm calling BF. You don't have to worry about what's inside the machine. You can just, you know, take it as you put something in and something else comes out. And we get this. A comes out. A didn't change. I let it pass through. But look what happens to the second register. There's that XOR again. This is the exclusive OR. Again, it operates the same way as it did in the classical world. Okay. And notice F of A, this is what the machine, that yellow box calculates. It calculates a number. And a function, what does it do? A function gives you a single number output, right? That's what makes it a function. It has to pass that vertical line test, which means the output is just one number, okay? Just one number. And in our case, we know it's either going to be a 0 or a 1 because this is computer world and computer world is binary, okay? So it's going to be a 0 or a 1. So what happens when I take the XOR with a minus sign? Well, let's have a look, shall we? This is what it is when you expand it, right? The minus state is 0 minus 1. So this is essentially just an expansion of that first box, okay? All I did was write it out. We haven't done anything exciting yet. So what if this is true? Let me see what you have to take a guess. What do you think is going to be the result here? F of A is saying I took A, whatever A is, it could be a single qubit or a whole mess of them, and I'm stuffing it into a function and I'm going to turn a crank, just like you did in your algebra class where you take X and you put it in the function and the function says, do this math, and here's an output. That's all. Just give me an output. Okay. So here it is written out. If f of A is 0, then the first term here, 0 XOR 0, is 0, right? Because the truth table says that either one is true, but not both. Well, if something is 0 and 0, they're both false, so the overall is false. 0 XOR 0 is 0. But here, 1 XOR 0. Is one or the other true? Yes. First one is. So this one's 1. Notice it's 0 minus 1. So let's talk about the second one. Now that you've seen an example with this one, what happens if f of A is 1? What do you think will happen? And I'm seeing a lot of right answers. Well done. Yeah. And unsurprisingly, you see this, because this time f of A is 1. So this overall computes to 1. This overall computes to 0, because remember, it's exclusive, not both. Well, both are 1s here, so that's not allowed. So what do you notice about this? This one and this one are opposites, aren't they? Okay, I'll give you a moment to read that. I want you to pay particular attention to the way I wrote it, this notation. This is extremely popular. This is extremely common. So this notation, the way I wrote it as -1 to a power of f of A, because remember, f of A is just a number. It's either 0 or 1, right? This will tell us whether or not that -1 stays a -1. If it's -1 to the first, it's just -1. And if it's -1 to the 0, guess what? It's 1, right? So I'm going to be quiet for a moment and let you really absorb that orange box, because that notation is extremely important. Okay. So we're going to use this again and again. This notation of -1 to the f of A. It might not always be A, sometimes it's X, but the point is -1 to the power of a function's output. That's the important takeaway here. So to conclude our little, why is this not working? Come on. Okay. So to conclude our little phase kickback review, remember, A is a string. It could be a string of length 1. It could be a string of length 50. It does not matter. It's a string. Okay. The function BF, it's just a machine. It's just like your algebra 1 functions. It is a machine. You give it an input, it gives you an output. That's all you need to know. Okay. And by using this XOR, this exclusive OR operation, we can track whether something is successful or not with the phase. And this last bullet point is kind of one of the magical pieces of Grover's algorithm, and we're going to get to see this in action today. What is an oracle? This drove me crazy when I was first learning this topic because the word oracle means something that can predict the future. That is what the English word means. That is not how this word is used in quantum computing. It's not. Instead, you can think of it as a black box, a machine that takes something as an input, or lots of somethings as an input. It does something, it makes a calculation, and then it makes a decision about the input, and then gives an output. Usually that output is true or false, 1 or 0. That's all an oracle is. It's a machine that makes decisions. At least for this class, okay? Right now, we are not going to worry about how the machine is made, how that machine is constructed. The important part for us today is that it works. And sometimes that's good enough. Okay? If you want to just think of it as it's a decision-making function box, great, I love it. Okay? But it doesn't predict the future. This drove me crazy. True story, ask my husband. And we can ask it as many times as we want. It's just a machine, so you can hit run again, run it again, run it again. You can do that, that's okay. In fact, sometimes you have to do that. The number of times you say, hey, I want to know, is this true? Is this true? Is this a good answer? The number of times you have to do that before getting a true answer, that's part of complexity theory, and we're going to get into that more later. But for those of you that have heard of such things, this is how this is involved. Can we assume that an oracle as an intelligent agent or machine learning? I don't know about machine learning. An intelligent agent, I suppose if you wanted to think of it as a little man inside a box making decisions, sure, but you can also just set it up as a machine. After all, a function, like a mathematical function from algebra, where you said x squared plus 2, that is potentially what you might be using. Or maybe it's a machine that when you give it input, and maybe it's an oracle that can answer questions that are like true false type stuff. Like you say, what time is the time? I got to come up with an example that's appropriate. Is 3 p.m. in the afternoon true or false? 3 p.m. Well, that's true. That is in the afternoon. Is 3 p.m. in the morning? Okay, that's false. It doesn't have to be intelligent. Okay. Let's define what an unsorted search is. This is the problem that Grover's algorithm solves. So we better discuss it, right? Some of you may have heard of this, especially if you come from a computer science or computer engineering background. But for those of you that haven't, let's make it, oh goodness, these pop-ups. Okay, how do we ask a computer to do a search? We encode criteria in Boolean logic, right? Boolean logic has operations like and, or not, and they use them in different combinations. So for example, if I wanted to search the library or Google or whatever, I would say, I want the word quantum in the title, and I also want it to be something that was published in 1994. But I don't want articles that have the names Sagan or DiVincenzo. I don't want them. These are search criteria. We can encode these as Boolean logic. And then if you wanted to do it symbolically, this is how you would do it with mathematical symbols. And we can ask a black box, a machine, can you find something that satisfies all of these criteria? I want quantum in the title, published in this year, but not these authors. And so I asked the black box, hey, I've got an idea. Is this what you're looking for? And it says, oh, well, you know, it isn't because it failed one of the conditions. This paper was published in 2005, so it failed, and it returns, nope, false. Now, if I give it another paper and I say, hey, this is Shor's algorithm, the first paper he published about his, you know, the article with his name, it's got quantum in the title. It's published in 1994. And it does not have the name Sagan or DiVincenzo. It does have the name Shor. This is a true result, full marks. That's what the black box is doing. It says, does this satisfy my criteria? Yes or no? That's all it does. Yes or no, true or false, 1 or 0. I've just said the same thing 3 times. Okay. And then we return them. If the answer is just one truth, then we return that. If you get a whole slew of articles, you might get a whole mess of them. We didn't have to know how the box works. We don't have to know how the function works. It just works. There are people who have to make the box work, no argument. Yes, that is an important part. But for today, you and me, we can pretend like it's just a happy box. We don't have to look inside. You can think of it like Google. I'm sure many of you use Google or DuckDuckGo, other search algorithms. When you use a search routine, I bet most of you don't think about, well, gee, how is Google doing this? We're just happy it works, right? You can treat this the same way. Classical sorted and unsorted search. Again, some of you may be familiar with this. So a sorted search, the data have been organized according to some characteristic or metric. There is structure here. It makes searching easier. And there are different algorithms depending on that structure. And this kind of makes sense from a human perspective too, right? We have different ways of looking for things depending on what we are looking for. Computers work the same way. Some search algorithms are better than others for given purposes. And some are more efficient than others, even if they do the same thing. Some examples that some of you may have heard of are things like binary search or interpolation or hash maps. These are all terms that if you've taken any computer science, you've probably heard these words. Okay, so here's an example that you have experienced in your everyday life. Find a specific word in a language dictionary. You know, if you speak English, then it's Webster's or Merriam-Oxford, and I mean a physical book. We're not cheating with a computer here. If I give you a dictionary book and I say, find this word for me, well, you're probably going to do this in a logical fashion. You're not going to start on the first page. If I ask you for a word that begins with R, you're probably going to open to the second half of the book. And you know that because the English alphabet is ordered a particular way. You know that as a human. And then you can get more specific. But you already know the second half is probably where you want to start, right? In a similar way, a computer would use a binary search for this. First half of the alphabet or second half, and then it goes in half and then half again. Cool, so that's sorted search. What happens if it's unsorted? There's no structure to the data. I just piled a bunch of stuff and I said, go find something. Not organized. The only way that we can find what we're looking for is kind of a random guess and check. We have to say, well, is this what we're looking for? Does this match my search criteria? No? Next one. It's random. It's ugly. Or we have to sort them first, and I'll say something about that in a minute. Let's say we have a pile of 500 unlabeled books, and they all look the same, and I want just one of those books. How are you going to do that? Think about it. Your teacher has given you 500 books. They all have different titles, but you need to find one. You would have to open every single book until you find the right one. That stinks. Now, you could sort the data first. There is always a way to structure your data. It might not be the best way, but there's a way to do it. But then you still have to spend time sorting it first, don't you? You still have to go through the process of opening all 500 of them, organizing them a particular way, and then on top of that, you still have to use a search algorithm. Did it help? Now, sometimes this is the right thing to do. If you have a database of employees and you need to keep organizing them because people join or leave your company, you need to keep on top of this. So it pays to keep it sorted, right? But sometimes it doesn't. Okay. Right, linear search. So somebody in chat said this is linear search. This is linear search. Linear search is I pick up something. Is this it? Nope. Because it's linear. For every object that I have to search through, I have to do a search. I have to open the book, right? It's a one-to-one. So how well do classical computers do this? Well, not well, because again, if there isn't structure, if we haven't organized the data, it's random. And we have no way to improve as we go. You could say, well, if we've already looked at something, then we don't have to look at it again. Okay, yes, but you're still doing a lot of work, aren't you? I could get lucky on my first guess, but if I'm not lucky, it will be it will be the last thing I look at, which that's allowed, isn't it? Now, you could say, strictly speaking, if I have 500 books, if I check book number 499 and that isn't it either, I know that it's book 500. But does it really matter at that point? I mean, we're splitting hairs at this point. So it's n-1. Ooh, yes, you saved a bunch of time, didn't you? What if it's more than 500 books? Hey, I don't want to do this. So is there any practical sense to use unsorted search? Well, I mean, it depends on the situation, right? If you're using a directory of people, you want to, and maybe you're setting up a company for the first time ever. I don't know. Yeah, you need to, that would be a good thing to sort, right? And then you can use a structured search algorithm. But what about unstructured search? Is there ever a reason for that? Like ever? Well, maybe you have a big pile of data and you are very confident that maybe you just need one piece of information from it, like one phone number from a whole mess of them. Okay, maybe that's the case. Off the top of my head, I won't lie, I can't think of like a reasonable example in the real world. I don't know if that's because maybe they don't exist or maybe because I'm not being creative enough. But this is a problem definitely in computer data. Actually, this is probably something that comes up in data analysis and data science, right? If you are handed, let's say you're doing web scraping or web trawling and you have a whole bunch of data. What's the first step that all data scientists have to take? They have to clean their data, right? They have to sort it. They have to provide structure. But what if you don't care about trends or anything? What if you just want to know how like one particular person interacted with the internet that day? Well, that might be it. Yeah. Okay, and this is how it scales. Okay. And it turns out that quantum computing can do better, and that's what we're going to see today. Okay. This is known as quadratic speed because it's, it's that factor of 2. All right. We made it, guys. Here we go. Grover's algorithm. We are going to start. I should offer a caveat. In a lot of other pedagogical material that I have seen that teaches this, I'm going backwards. Most people start with a particular implementation of the mathematics. I'm starting with a picture. And I'm doing that on purpose. A lot of other sources already do the here's the equation form, and they do the picture at the end. So if you like that version better, go find it. I like this version because you don't really need a ton of math. I know that for a lot of people, math is kind of scary or intimidating. I know that. It's unfortunate because math is quite pretty, and if taught in a more calm and relaxed manner, I do think that more people would be comfortable with it. But the truth is, math scares people. And quantum math is not like regular math. There's these superpositions and tensors and coefficients and phase. And like, who has time for that? A picture doesn't have any of that. So this picture, if you can do addition, subtraction, multiplication, and division, we're set. And I like to think that all of you at this point in your life are experts at all 4 of those types of math. I guess there's the hardest math in what we're about to do is taking averages. So that's why I like to start with this. We'll still go through the math, but let's start with the picture. I have 2 main learning objectives for what we're about to do. The first is I want you to notice that each guess that we take, each iteration improves the next one. This is not like classical unsorted search. In a classical unsorted search, if you take a guess and you're wrong, it does not help you with your next guess. I guess you could say it removes an option from the pool, but that doesn't count. Because that's kind of almost the trivial benefit. doesn't really help you make your next guess. This one will. And we're going to see that. So keep an eye out for that. And the second one is, and this is something that is not unique to Grover's algorithm. This is a ubiquitous idea throughout all of quantum. It is an idea that I want, it doesn't matter whether you're doing chemistry, physics, computation, sensing, I do not care. Quantum does not explore all options at once. It is not that Schrodinger's cat is both alive and dead. It isn't. That doesn't make sense. Cats cannot do that. I don't care what you've read on the internet about cats. They don't do that. But what does happen is we look at the probability. The probability can be more than one thing, because that's what probability is. It's a chance that we have one case or another. That is what we are doing here. And I think that these pictures really ram this idea home, that we are not exploring things all at once. This isn't a massive parallelization scheme. We are using quantum mechanics to probabilistically look at everything and say, there is a probability of all of this happening. The idea behind Grover's algorithm and many other quantum algorithms, not just here, is that we want to use quantum mechanical superpowers of things like entanglement, interference, phase kickback, to manipulate those probabilities in such a way that when we get to the end, the most likely result is also the true answer. That is what we are doing. And if that idea is still a little too philosophical for you, that's okay. To be honest, most people start with the idea of it's everything all at once. That's actually how most people start. It's a mental crutch because we don't have, in classical reality, we don't think this way unless you're like a statistician, maybe. This takes time to really internalize. But the sooner I start introducing it to you, the faster it will catch on. At least that's my hope. Okay, I have blathered about that far too much. Yes, PKB is phase kickback. Thank you for catching that. Yeah. Okay, I'm just going to quickly, it's been a minute since I looked at chat. To answer, I don't know if distributed systems approach on Grover's algorithm. I'll admit I don't know what that would look like, so I can't offer an appropriate answer. Okay. Okay, doesn't look like there's anything really someone say still boggled by the results from the previous guess and prove the next one. We are going to see that next. You will actually have a visual proof of it and a mathematical one, but visual first, because I like pictures. So let's set the stage for this problem. Let's say we only have 8 options. In other words, 3 qubits, right? 0, 0, 0, 0, 0, 1, all the way up through 1, 1, 1. So I have 8 options. Now, yes, I know that unsorted search through 8 options is not the end of the world, but you can extend this to as many objects as you like. It's just that as humans, 8 is a friendly number. 8 is a good number. It's big enough that we can say, oh, yes, there's an advantage, but it's also small enough that we as humans can still conceptualize and draw pictures of it. Now, it could be the case that more than one option is correct, but here I want to take the hardest case and say only one of these is right. That's going to be the hardest case, right? Because the probability of getting just the right answer for an unsorted search on a classical computer would be 1 over square root of 8. That comes out to about 12.5%. Can a quantum computer do better? Okay. When we start, we assume that everybody is in equal superposition. In other words, everybody has an equal chance to be the guess. That makes sense. Okay, these are my probability amplitudes, alpha sub x. So for a given string x, like 0, 0, 0, that's what this will be, okay? That's all that is. That's just a generic probability amplitude symbol. Okay, there we go. We have 8 choices. Only one of these is correct. There he is. Now you and I know that. The computer doesn't. Equal superposition, right? They all have the same coefficient. And now I'm going to ask the oracle, hey, which one of these is right? Now remember, this is a machine that's doing something that I can't see. The oracle is encoded. Remember what we said when we looked at this picture? It was like several slides ago. We said it can store information in the phase. This is it, guys. It's storing it in the phase. The magnitude did not change. The phase did, and this is a quantum mechanical effect. The values didn't change. The sign in front, SIGN, did. I am marking the one that is correct. I'm saying, hey, this one's right. Okay, great, we did that. We used phase kickback. What does this help for? Okay, great. Now it's upside down. Wonderful. All right, well, let's compute the mean of all those amplitudes. Let's compute the average. Ta-da! And I've estimated this. This is not to scale. I didn't have that kind of energy. Okay. Now let's execute this math. I'm going to give you a few seconds to look through it, but basically it's 2 times the average minus the individual amplitudes. Somebody is asking, how do we tell the oracle that 101 is correct? You do not have to worry about that today. There is a machine that knows that 101 is correct. The machine knows. And we ask, is 000 correct? And it will say, no, it isn't. And is 111 correct? No. The oracle is a black box. There are people who have to design oracles. That's part of quantum algorithm development. Today, we are not interested in that. It is a machine. 2 times average minus 8. No, it's 2 times average minus the amplitude, the individual amplitude. I don't know if you guys can see, there's a square root here. Okay. And remember, if there were more than 8 options, the amplitudes would be different. So that's why I'm using a symbol as opposed to a number. Some of you might already see where this is going. Look at that. Take a look at this. I'm going to be quiet for a minute and let you guys process this image. Why is 101 correct? Because I said so, and it's my example. That's all. Maybe 101 corresponds to the book name that I'm looking for. I numbered 8 books, and I said, this book is 000, this book is 001. I just gave them names. I picked 101. It's a good number. I don't understand the slide. So we started with, this is the average. This blue line is the overall average. I execute this arithmetic, basically, and this is what I get. Remember, each of these heights, that's what alpha sub x is, the height, the magnitude, okay? This height is alpha sub x for this bar. This height is alpha sub x for this bar. This height is alpha sub x for that one. Okay, that's all. And using very basic arithmetic, we can get this. Pretty neat, huh? So to go back to an earlier point, this makes our next, so if I were to take a guess on the previous slide, if I said, I'm going to guess at random starting here, look at the probabilities. I have a 12.5% chance of getting the right answer because it's 1 out of 8. But here, the probability is higher. That's better. And if I do this again, I'll improve it even more. See? Why do we have to compute 2 mu alpha x? Because that's how the algorithm works. Why can't the oracle just give the answer directly? That's not how oracles work. They just tell you, is your guess true or false? You have to ask it questions, though. So there was a question, and it's flying past. Come back. Can we interpret this that that we initially isolate the correct answer and then perform operations on the rest of them to decrease their probability, which consequently increases the probability of the correct answer? In a sense, yes. In a sense, the oracle is what lets us do that. The oracle knows whether or not something is correct or not, and it tags, says, hey, this one's right, make its probability higher. Yes, so Sarana has a comment. You have the oracle that tells you which index in this case is the correct index. Yeah, this is the one, this is with the phase kickbacks. That is exactly what is happening. The oracle tags the right answer. This is all invisible to you and me. Because again, the black box is, the oracle is a black box. I can't see inside. Okay. So every time we do this, we get better. And this goes back to the idea of like, hey, this may be an unsorted search problem, but every previous guess improves the next one. This is so much better than classical. Hooray, we did it. Now, word of caution, it is possible to overdo this. If you might say, why don't we just apply it 50 times and be done? Well, there are reasons, and we're going to look at them later, not right this second, because that's getting into some of the nitty-gritty math, which is coming up, so stay tuned. But you can't just apply it over and over and over forever. Okay? Because what ends up happening is if you apply it too many times, it's like you overdo it, you overshoot, and then you get garbage. These things happen. I want to emphasize this again. We never explored all options. We are manipulating probability. The cat is not alive and dead. There is a probability that the cat is alive or that it is dead, but we don't know until we look. Okay. Let's talk about Grover's algorithm in terms of like broad strokes, big picture. Okay. There are three main steps. The first is we have an n qubit register, whether it's 1 or 50, doesn't matter to me. We start them all at 0. And we're going to use Hadamard gates to put them all in an equal superposition. And we have seen our first instance of one of those equal superposition symbols that I was using earlier. Okay. So there it is. Keep that in mind. I will point it out as we go, but I wanted you to just see it again because this is the first time we're using it. We are going to apply a magical unitary transform. Well, it's not magical. This is Grover's unitary matrix. We will define everything that's going on in there in a moment, but this is the thing that we iterate. We're going to apply this a certain number of times. It turns out we're going to label that number of iterations K, as in kilo. These are all operators, which is to say they are all matrices. To make it a little easier to read, I'm going to remove that hat. Strictly speaking, you shouldn't do that because symbols have very specific meanings. But the truth is that typing it up in Google was a pain in my butt, and I didn't want to do it anymore. Remember what I said about everyone's lazy? Me too. These are also operators. We'll get to that in a minute. There are ways to compute K. We'll get to that. Hold off with that for now. The third and final step is we measure. We observe. And we get an output. If we did everything else correctly and we had a good computer, coherent supercomputer, we would get a true result. We would get that answer 101 with the highest probability. This is why we have to do multiple trials, because what if I do one trial and maybe there was only a 1%, maybe the true answer was at 99%. That's great. What? But that's not perfect, is it? What happens if I take my observation and that 1% chance of getting it wrong is what I see? Well, that stinks. So you have to do this multiple times. So what does the circuit look like? And again, we are not going to spend eons on this, but for those of you that are more circuit inclined, let's have a look. So again, the top register in blue, That is a whole string. It could be 1 bit, it could, or 1 qubit, or a gajillion of them. I don't care. That second qubit is, I'd like to know why I wrote -1. That's a typo, excuse me. I will fix that. It should just be a minus sign. Never mind, or a 1 rather. It should be a 1, not a -1. I don't know why there's a minus. You know what? That's going to bother me. I need to fix that because we don't make mistakes around here. Okay, back to the show. Bothering me. Okay. But actually, this time, the first step we said was put everything in superposition. This is an equal superposition. We are now going to apply the Grover unitary matrix with trumpets and fanfares and confetti. Okay. That is G. And remember, we said it had some components with a ZF and a Z0 and some H's. We'll get to this, but that's the whole thing. So this equation a minute ago, this thing in bold, that's in the orange box. And you might say, Erica, why is there a dashed line inside? What's that? That is a specific component called U. And we'll define that in a minute. I just wanted to show it to you in a picture, okay? We have to do this. We have to apply G several times. I don't know how many, but it's got to be more than 1. And then we measure. And then step 4, profit, right? That's what the cool kids say, step 4, profit. Anyway, I'm not that cool. Okay, God, I have 2 typos. Okay, I will fix that. In the meantime, who can tell me why that qubit, why that quantum register is in 1, where all the others, X is initialized to 0, whether it's 1 qubit or 50, they are all 0. Why is this one different? Who can tell me? I imagine a lot of you, so. I see one answer so far. Who else? Good. Yeah, it's because we're going to use phase kickback. In order to have phase kickback, or PKB, you need to have something with a phase. Something that is different than the other one. Strictly speaking, if we define these phases inverted, if everything else was set to 1 and this one was set to 0, sure, we could have that discussion, but like, why do that? That's needlessly complicated. I mean, you know, we got stuff to do. Quibbling over like details like that is not useful. So yes, we use 1 because when we put that into superposition, it will have a phase that is different than the other register in blue. So blue and red will have different phases relative to each other. This is probably something you've heard before. You will hear it a million more times, and it will probably take a few weeks or months for it to sink in. And that's okay, that's normal. Phase is something that you measure relative to each other. Okay, so for a given system, that system has a phase, and don't worry about what's over there. If your friend Joe has his own system, great. He's going to have his own global phase, and I will have my own global phase because it's my system. Okay, but if I have one qubit and another qubit, their phases are relative to each other, not Joe's over there. Joe is a cool guy, don't get me wrong, but whatever he's doing over there has nothing to do with my little world. Unless we're networked, but we're pretending that we're not, okay? My stuff is mine. What are those Z operators? They're oracles, but they're also operators, which means they also have matrix representations because all operators are represented as matrices. So here's that algorithm. Here's that Grover unitary matrix again. Okay. Z0 or Z0 negates the phase if and only if the input string is all zeros. It's just, that's it. Okay. Nothing earth-shattering here. ZF encode, and then the other one This encodes the oracle function f. Oracle function f tells us whether or not something is a desired result or an undesired result. F tells us, I'm going to repeat that, F says these are the good answers, whether there's 1 or 50. These are the bad answers. It is the decider. We encode that in ZF, and we do it with phase kickback. So I'll say that part again too. ZF is the part that says right here, if it's true or false. It is going to give true, 1, or 0, false. And then we're going to stick it on a -1 as a phase. Remember I said this notation was gonna come back, and it's very important? Here it is, guys. We made it. This is important. All right. Okay. Lots of questions about cats. Okay. All right. So I want you to really pay attention to ZF in particular, because this is why we spent so much time talking about phase kickback. This is why it's useful. So I'm going to give you a few more seconds to look. Also, it was time for coffee. There is a matrix representation for this. Okay. It's the identity matrix with a -1 for the all 0 case, which is that first column, right? We can write this a different way, where that big bolded number 1, that is the identity matrix in this PowerPoint. Normally, this is an unfortunate consequence of computer font. I could not find a letter I for identity that looked right. They all looked like the letter L, the English letter L, and that was driving me crazy. So for this talk, a bolded number 1 like that means the identity matrix, okay? 1 is the identity. I know that's not the way most textbooks present it. I am sorry. I got into a fight with Google. These are Google slides. And after fighting with it for 10 minutes, I said, this is not a good use of my time. So that's what's going on here. So let's do math. I want to draw attention to the reference box in the upper right-hand corner. Okay. That's there to be referred to. It's your cheat sheet. Okay. So that's just a summary of everything on the previous 2 slides, but without the explanation. So we have that G thing. Okay. I'm going to re-express it. Remember a little while ago, I had that sub box in gray. We're going to call that U, as in umbrella. All I did was define this. Okay. Nothing crazy yet. Promise. We just made a substitution. Okay. If you work through the math, which we're not going to do here, but if you were to sit down and distribute this through Z0, the definition that I gave in this upper box here, if you sit down and do this, you'll get this. I promise. Promise. Try to work through it yourself. You'll surprise yourself. You're actually better at this than you realize. It's just math. Okay. Again, 1 is the identity. And if you continue to work through this, if you expand it instead of putting it in bracket notation or Dirac notation, if you expand it out as a matrix, you get this. Okay? Nothing too crazy. Okay? Bro, fight with Google to find a font. No, no, I'm not. I did fight with Google and it didn't work. I lost. I'm okay with admitting that. Know when to pick your battles. Okay. That was not the hill to die on for me. We now have 2 new things. Let's define a friend. This is going to be important because we said this is inversion about the mean. So we better define a mean, huh? Take a look at the top box. This should not be earth-shattering to anybody. Take a moment, think about it. This is just an average, the one that you learned when you were a kid. We just wrote it in a slightly fancier way. Okay? It's just an average. Add everything up, divide by the number. That's it. And we're going to call it mu, the Greek letter. By the way, in this implementation, because it is inversion about the mean, that u, the negative h, or the negative Hadamard Z0h, that's called the diffusion operator. Okay? So now you can go to parties and tell everybody this cool fact you learned, and you will be the big hit at the party, right? Because we all go to those kind of parties where this is interesting, right? What, you don't? Okay. Okay, so this is from the previous slide. The top line here is from the previous slide. Okay. So when I plug it in, when I apply u to this, what is this? This is just state vector, right? It's amplitudes and their associated kets, and it's a sum of them. Okay, nothing too crazy. This is coefficients. These are scalars, so they can come outside, or rather, this can go through, right? Coefficients just come for the ride. They're just amplitudes. And now, remember, we said that u is equal to this mess in here, right? I'm just plugging in. It's just a substitution. Okay? Still with me? More or less? More or less. When this cleans up, remember what we said the previous slide, what the mean was? Let's look at that again. It's 1 over n of the sum of the indices, or of the, oh wow, of the amplitudes, right? Well, 1 over n times the sum of the amplitudes. That's just the mean, isn't it? Yes, there's a 2 and some other stuff, but look, we can pull this n out. It's just a coefficient. It's a number. So I can pull that out, and that becomes mu. The 2 comes down for the ride. And I felt like converting this back because I didn't feel like writing all that out. Okay. Remember, when you might say, Erica, wait, where's that amplitude from? Don't forget, distribution matters. We distribute it to here, and we distribute it to here. So that's why there's still an amplitude down here. Okay. Cool. So this is the u part. All right. We started with this, with 4 operators. Hadamard, Z0, Hadamard, ZF, 4 operators. And we split it up like this. And then we did some finagling and tinkering to make u a little more sexy. So this is what we ended with on the previous slide. Okay. Now, what's left? That ZF thing is still there. Apparently I forgot to put the reference sheet on this one. So let's look at the reference box up in the upper right-hand corner. Remember what ZF does. Okay. So if I substitute that exact definition for ZF, I get this. Huh. This should look kind of familiar. This is what we were showing in the pictorial representation a minute ago. And this is just either -1 or 1, right? This is not like crazy stuff here. This is a plus or it's either a -1 or it's a +1. Think about the way we did inversion about the mean. We flipped something, the right answers got flipped upside down, the phase got inverted, and then we did this thing where we doubled the mean and subtracted the individual amplitudes. Can you see it? Take a minute and just think about this. Now remember, we apply G multiple times, so this isn't like a one and done. This is the operator G. Here are the 2 things it does. And you apply it several times. Take a look. I'm going to be quiet for a minute. Now, if you're like, oh my God, that did not make sense, holy cow, that's okay. We are going through this relatively fast. Truly. So it's okay. Don't panic. Besides, you can always watch this video again and you can pause me and everything. Let's do round 2. Now, preface. Round 2 has a lot of math coming up. We will go through it. You know what? I better check about timing because I think I was supposed to be done 15 minutes ago. Someone from Womanium, can you please tell me what the timing is looking like? Because I am already 20 minutes over time. And I don't want to, yes.
Please feel free to keep going. I heard that people love the more detailed explanations, and we will upload this recording to everyone who needs to leave now and for whom it's getting too late.
Yeah.
But this great lecture is very important to have for everyone. So please keep going. If it's too late at your place, you have to do other things, feel free to leave. The recording will be available.
Okay. I don't want to rush what comes up next, but I completely understand that, like, you know, people have time and jobs and lives. In some parts of the world, it is Friday night, and I am the last thing between you and your evening. I get it. And for some of you, this might be right before bed. I get it. For me, in the United States, it's like noon. So if you have to leave, I will not be insulted. Go do your thing. This lecture will be posted. Back to the lecture. We are about to go through a lot of math. Now, before everybody panics, you know, we don't need screaming crazy people. The first thing I want to say is that the individual steps are simple. They truly are. We are going to go through each of the steps, but I have discovered that when you do long algorithms in a math classroom or in a science classroom, people sometimes forget the big picture. They get so in the weeds that, like, the little pieces and the wheels start to come off, and I get that. I will try to keep reminding you, hey, this is why we're doing this, or now that we've defined this, how does it fit into the big picture? But if this is like a fire hose and you were given a straw, congratulations on being normal. Okay? The individual pieces will make sense. The big picture is hard to keep track of because there are a lot of pieces. So with that caveat, let's go. Remember this slide from a couple of minutes ago? It's back. But this time we're going to focus on this. Last time we said negative h, z, h. That was the diffusion operator. This time I'm going to rearrange it, right? It's associative, so I'm just going to move those parentheses a little bit. We'll get to that in a minute, but just a heads up. It's all the same math in a way, because it all comes from this operator. This operator didn't change, but we're going to group it differently. That is the main difference in these two ways to understand it. It's the same algorithm, the same operator, grouped differently. By the way, there is a pictorial representation for this too, but this time I left it for the end because you kind of need to see what's going on mathematically to understand why the picture works the way it does. So the very first thing we need to do is define what is a good string and what is a bad string. Okay, and I've just written this up in real plain English, okay? A good string is one that satisfies the criteria. It's a true answer. Okay, great. Whatever those criteria are, I don't care. That's in the oracle and that's a black box. Whatever it is, they are true. Bad strings don't. So some will return true if they're good strings and 0 false if they are bad strings. By the way, I probably should have said this a million years ago. 1 and true are logically the same thing. So if I say 1 or if I say true, you can substitute the other word. Same for 0 and false, okay? Just in case I forgot to say that. Okay. Okay, let's talk about what I just put up. So we have our good strings and our bad strings. Cool. But I can't tell a computer, well, this is good. Computers don't like that. They like 0s and 1s and things like that. They like math. So we have to translate the words good and bad into math, and we do that using vectors, okay? So the set of A is all the strings that satisfy the criteria such that we get a true result. So in math terms, The set of A for this is the set for f of x is a string that is n qubits or n bits long, such that when we put in x, whether it is 1 qubit or 57, we get 1, a true result. Okay? And little a is that number of true results. So if big N, or I'm sorry, yes, if big N is the number of options that I have, like earlier it was 8, little a is the number of correct answers. In the previous example, there was just 1 correct answer, so little a would be 1. Okay. A bad set is equivalently, by similarity, the exact same thing, except it's going to give a function value of 0. For those of you that are a little bit like you're catching on a little faster, think about how we defined this in terms of PKB that's coming down the line. Okay. Remember, ZF encodes the phase information in that power, -1 to the power of something. Think about how this 1 and this 0 are going to impact that. Just something to tool around with in the back of your head. Okay. To finish the thought, little a plus little b equals big N, the number of options. So in the earlier example, this would be 1 plus 7 equals 8. Okay, nothing too crazy. Not yet. Who can answer this? These sets are orthogonal. Why? Who can tell me? By the way, I don't mind if you're guessing and you're not sure, like, go ahead, speak up. This is not a test. Good. I see a lot of good ways to phrase this. One person said that the inner product is 0. True, because the vector representation, if we were to represent the strings as vectors, they would come out. The inner product would be 0. Another person said a state can't be good and bad. That is basically the reason. What we say is these two sets are disjoint. That's the fancy math word. My mom was a math teacher, so sometimes that leaks into my way of speaking. Thanks, Mom. Okay, so these are disjoint. They don't share anything. There's no overlap in the Venn diagram. A state can't be both, an answer can't be both true and false. That doesn't make sense. And this is why the cat can't be alive and dead. Sorry, I have a problem about that because it drives me crazy. Okay. Let's keep going. So now in our reference box, now we have some new friends. That's basically the summary of the previous slide is just in that box now. So now let's define them as vectors. We have our sets. Computers don't like sets, they like vectors. So let's do that. Remember, little a and little b are the number. They are integers. They're real numbers. If we're getting really persnickety, well, I guess integers are real numbers. But anyway, the point is that they are whole numbers. You can't have a fractional answer. That doesn't make sense. So they are normalized according to this number, right? If there is 1 correct answer out of 8, right? Still with me? So take a look. So set big A, okay? Notice that this is not bolded. This is a set. This is a vector string. Notice the difference. I try to be really careful with my symbols here. There is nothing worse than somebody who gives a lecture and uses the same symbol 5 different ways. That's, I have nasty thoughts about that. You can do whatever you like in your notes, but if you're teaching, that's not acceptable. Anyway, okay, so A is the normalized sum. So it might be more than one string. After all, if there are more than one right answer, then the vector that represents them should have more than one addend, right? This is just a shorthand to say all of them, whether it's 1 right answer out of 50 or 10 right results out of 50. This symbol will capture that, and these are all the wrong ones or the bad ones. B for bad. Okay. So what about the overall state function or state vector, excuse me, psi? Well, okay, let's represent it like this, where we have alpha and beta. Alpha and beta belong to the set of reals, and they satisfy this, which is to say that, and this is something that should not be profound, but it kind of is in its own way. We are saying that of all the strings, whether they belong to set A or set B, all of the solutions in A, all of the solutions in B, when you sum them together, you get 100%. That's what this is saying. That's it. That all of the answers are all of the answers. Ooh. But it's still very important because it gives us this rule. Okay? The goal of Grover's algorithm, here it is, kids. The goal of Grover's algorithm is to manipulate these probabilities, alpha and beta, such that at the end of the algorithm, at the end, not in the middle, I don't care about the middle, right? At the end, when I take a look at my qubits, the result that I get is the highest probability of being one of the members of the good strings, whether it's 1 or 30 or 700, I don't care. As long as we get one right answer, we are happy. That is what we are trying to do. Why is it alpha squared plus beta squared equals 1? Because they're probability amplitudes. Okay. It's like kind of similar, like when you have superposition, you have like 1 over square root 2 plus 1 over square root 2, like that. That's why. So now we got this. Remember this? I said this was going to come back. Remember, there were 3 different ways to write it. I want to emphasize that because in some places it's more convenient to use one, it's more convenient to use the other. So I'm going to emphasize here are all 3 again for your viewing pleasure, right? I want to express the equal superposition in terms of A and B. Why? Because when we start the algorithm, everything is in equal superposition, which is to say that even if we only have one right answer and everything else is wrong or it's half and half, at the beginning, I have equal probability of selecting any option, whether or not it is good or bad. Does that make sense? I'll say it again. At the very beginning, I have all of the options in front of me, and if I pick one at random, then the probability of picking that one versus its friend or something else is all equal. And I don't know whether it's true or false, if it's good or bad. At the beginning, it's all equal superposition, which is why we're going to write this even if A and B are different sizes, they're still an equal superposition, okay? So I want to do this. Who has ideas? What should I put in those, in the blank spots? Okay, I'm seeing some good guesses, but there's a couple of pieces missing. Remember, these are different sizes, right? Set A has A elements and set B has B elements. Right? It's this stuff up here. Little a, little b. How about that? Go through the math. If I square this number and I square this number, what do I get? I get a squared. Well, I get a squared over n, right? And right? You see how that math all works out? Okay. Hooray! We got there. typo. I'll have to look at that later. Okay, so why did we do all this? Okay, let's back up. Remember, big picture time. The big picture is I needed a way to think about good sets and bad sets such that a computer could handle it. But remember, the big goal is to apply Grover's algorithm. So all of the stuff we've been talking about for the last 10 minutes has just been, how do I express good and bad strings in the computer? That's all we've been doing so far. Now we get to the Grover's algorithm group. And by linearity, if I apply G to psi, like up here, I should have written this out. Nope, I didn't. Okay, when I apply G to psi, it's going to distribute, so I can apply it separately. That's because of linearity. So I apply G to ket A and G to ket B. So we're going to look at those separately. There's no reason to look at both of them at the same time. You'll just get upset. So let's just do this. And our reference box keeps getting bigger. Okay. Remember I said that G hasn't changed. It's still HZ, or HZ0, HZF. That didn't change. Okay. Remember I said we're going to group it a little differently? Here's the grouping. I know you're flabbergasted and shocked, right? I just moved the minus sign. That's all I did. Let's look at this thing. This first factor here. Let's just look at that using the definition of Z0 or Z0, okay? We're going to use the definition from our nifty little reference box, okay? Earlier in the first part, we talked about this representation of Z0. We're not going to go back to that right now, but if you're watching this like a recording, if you forgot where this came from, go back a few slides, okay? This is just an equivalent definition. So I'm going to just substitute. So to reiterate, I've got my H on the outside, my H on the outside, and Z0 is actually just like this. This is an equivalent definition. Again, one is the identity. We're going to distribute. Remember, we have to do distribution 2 times because there's one number out here and one number out here. I'm going to do them both at once to save some time. But you could do this in 2 steps, absolutely. I did it all at once. So the first thing here, this one, from the left, I get an H0. From the right, I get an H. I'm sorry, not an H0, goodness. From the left, I get Hadamards. From the right, I get Hadamards. So we have Hadamard, Hadamard. Okay? Minus, okay, the minus comes to the right. And then we distribute here. The 2 is just a coefficient. It's a scalar, so we can pass through it. Okay? That's it. This is ugly. I don't like it. Who can tell me what Hadamard Hadamard is? What is that? Oh, some people are jumping the gun. Well done. Yes, it is identity. Good. Good. What about that second thing? That's ugly too. I don't like it. Is there something else we can rewrite that as? Is there something more convenient as this second term here? Can I fix this? Well, it's not identity, it's something else. It is an outer product, that is true. For those that, for those of you that's a new term, an outer product is when you take a ket and a bra. That is an outer product. But there's also these Hadamards on the outside. Look to your reference box. Do you see anything in this reference box that might help? Not quite cancellation, but we are going to rewrite it like this. Okay? I told you it would come back. And you might say, why do we do this? Well, A, it's a lot cleaner, isn't it? But it's still just equal superposition. And sometimes it's just easier to read things when they're not cluttered. This is messy. This is cluttered. That's nice. And you might say, why couldn't we just skip to that? Because remember, up here, it wasn't distributed yet. We had to go through this process first. So we couldn't just skip right to the bottom. You had to actually work through it. You had to earn it. Hey, that's very nice looking. That's really simple too. Much cleaner. Good. Oh, this is the different partitioning. That's it. I know. Most people are like, oh, it was going to be like you move the parenthesis. No. It's still HZH. It's just a question of where that minus sign is. That is it. Okay. So I plug in what we got on the previous slide, right? This result at the bottom here. I'm going to plug that in. Okay. But I still have the negative sign with the ZF. Look to your reference box. Remember this? What is this? Who can tell me? Is PKB? Is there a phase flip? Think carefully. I know it's a little hard. I know. Yes, it is that. It's just that, right? Because remember, these are the good strings. The good strings, when plugged into f of x, will return the result true. That's at the very tippy top here. When I take a good string and I plug it into f of x, and anything that I take from ket A, anything that I take is a good string because I defined it that way. I plug that into f of x, and out I get a 1. Well, there's a -1, and then remember, this is -1 to the first power. -1 to the first power is -1, and this negative sign times negative, -1 times -1 is 1. Take a moment and go through that again because there was some moving pieces and like it's actually pretty gentle, but if you blink, you miss it. Yeah, there you go. So just go through the algebra again. I promise it's not that scary. It's just keep your minus sign straight. If you lose a minus sign, you're in big trouble. So keep an eye on those. So let's take the previous information and this information. Okay. ZF basically disappears. So all we're left with is that first bit. Let's distribute again. Let's, right, this is a minus sign, so I can apply this operator to A and this to A. Remember, an outer product is a matrix. So if it's a matrix, it's an operator. So this is an operator and this is an operator. Let's apply them both to the ket, or the vector, A. Okay, nothing too crazy. I just distribute it. 1 times anything, the identity times A had better be A, otherwise what? That's the point of an identity. What's this? And obviously I've kind of given away the plot here because I'm highlighting things. What do you guys think it is? By definitions and orthogonality. Remember we said they're orthogonal, which is to say that things cannot, a string cannot be both good and bad. Remember, H is everybody. H is the superposition of all good and bad answers because it's everything. A is only good. So what's going on here? I need to make a little comment. The reason I had to do this, this is another fight I had with Google. I could not get like a normal looking fraction bar to save my life. Of all the dumb problems to deal with, it's amazing. You can do quantum mechanics, but you can't get Google to format something correctly. And I didn't have the patience to fight with like Beamer or LaTeX. I know these things exist. I was on a clock. You make lemons, you make lemonade. Now, I want to point out that H, this is by definition, right? This is right here. So the green corresponds to green. I just expanded it. Green with green. Orange with orange. Okay? This is an inner product, which means an inner product just gives us a number, a scalar at the end. Not a vector, not a matrix, it's a number. That's a probability amplitude, isn't it? Okay. Let's clean that up. I don't want to look at that, and neither do you. Here's the final result. We are not going to apply G to B as well, because it's basically the same analysis with a couple of very minor differences, because of course B is not going to be the same thing for ZF. But if you do the same steps and work it through on your own, I encourage this, you get this. Very similar, a little different. Notice that this coefficient is here. You see how they flip-flop coefficients? Okay. Now, what's next? Big picture time. Why did we do all this? Who cares? Right? We've just spent like 10 minutes going through this operator. Why? Okay, well, remember we said that we wanted to apply G to the overall state vector psi. And psi is a sum of these two pieces, A and B. So we separately looked at them. And now we have nice, clean representations for both. That's why we did it, because I wanted to know how Grover's unitary matrix applied to the pieces. That's all, okay? So let's put it back together. We have psi, which is a sum of the good stuff and the bad stuff, right? Where these are the definitions, I just repeated them, there's nothing new here. So we wanted to do this, right? So we needed this and that. And the last like 2 or 3 slides, however many it was, oh, I thought I gave the definitions at the bottom. The stuff on this previous slide here, these 2 things at the bottom, that's what we were doing. Because we wanted to do this. Back to the show. Okay. We have our 3 steps. Superposition, apply the Grover algorithm matrix, measure. We define 2 orthogonal sets. We've expressed those as vectors in equal superposition because at the beginning, everything is in equal superposition. That's the point. We are trying to manipulate them. Okay. We defined the overall state vector. And then we have figured out how G affects each. There's the summary. Okay, I thought this was on the previous slide. My bad. Okay. Back into the weeds. Let's go. A quick life tip. And I want to call out, I was part of, I attended some lectures last year that IBM gave. Dr. John Watrous is like the director of technical education over there, I think, or he was at the time. He gave a wonderful set of lectures that I followed, and the following example is something that he explained in a very nice, neat package, so I have stolen that from him. The mathematics are true regardless, but the example that I used to demonstrate that is from him, so thank you. Okay. Label your, so for matrices, operators, remember matrices and operators are the same thing. Label your rows and columns in the same order. I'll explain that in a minute with a picture. Left to right, across the top, top down, going down the side, okay? Label them in the same order, so like 0, 1, 2. Don't mix and match, don't do that. When you want to know how a particular state vector transforms, find the column, and that column vector is the ket. So let's see an example. 2 conditions. If my input is 0, don't do anything. Leave it as 0. If it's 0 input, give the output of 0. If the input is 1, make it half and half. That half the time it will be 0 and half the time it will be 1. So what did I say? I said, label your matrix in the same order across 0, 1, 0, 1. This is a 2 by 2, but like, hopefully you can see how this would apply to larger matrices. 0, 1, 0, 1. This is how it will look. I'm going to be quiet for a minute and let you guys look. By the way, this is classical information, which is why we're not dealing with like square roots and superposition stuff. I'm not dealing with that. This is classical information. Okay, so real life. See if this makes sense. This is going to be important in a minute. If this already makes sense to you, I don't know, do some jumping jacks or something. It's a long day. We're going to use this. Okay, that was a little commercial break. How are we going to use this? We said a minute ago that we now have an expression for how G applies to A and how for G applies to B. That's great. You know what would be better? If we could express G as a matrix. Because after all, quantum mechanics does not work without matrices. That is the language to speak. I don't see any matrices here. So we need one, don't we? A matrix explains how a state vector transforms. So we better have one. Let's do it. Okay. This is, again, the same stuff. I've copied it now like 4 times. Nothing has changed. I want to preface what I'm about to show with a comment. This is not the intuitive way to write this. There is a very, very good reason we flipped this on its head. It is legal. For some of you who have taken linear algebra, you are allowed to swap rows and swap columns and the determinant remains the same. Remember that? We're kind of using that to our advantage here, okay? There is a good reason, and we will explain it. Remember I said you label it according to the same order? Here, I'm flipping it backwards. I'm doing BA, BA. You might say, Erica, why are you doing this to us? It'll make sense, I promise. This is how A transforms. When I apply G, this is how it transforms, okay? When I apply G to B, this is how that transforms. I'm going to be quiet for a minute and let you play that game in your head. Okay. I know it's a little weird to, why didn't I put it in alphabetical order according to the English language? I have a reason, and it's this. It's still a 2x2 matrix, it's just much tinier. These are the same. Notice this one is squared, okay? Which is basically like saying 2 matrices multiplied. It's not, you don't distribute exponentiation. That's not how this works. This is a matrix product. One matrix times another matrix. Take a look at this. Now, we're not going to go through this proof right now. We don't have that kind of time. I encourage you, though, start with this and square it and see if you can get this back out. You can, I promise. I checked it yesterday because I was bothered by this. Don't forget that a plus b, little a plus little b is big N. You will need that, okay? I promise. And that's why we wrote this way. We wrote this in a really backwards way because it's convenient because of what's coming next. Now, some of you might look at this and go, I've seen that before. I hope so. Not everyone, and that's okay. But some of you have probably seen something very suspiciously like this. I'll bet anything. It's a rotation matrix. When we are in Euclidean space, which is most of what most of you have learned in mathematics classes, unless you're doing like the really crazy stuff. Most of you have most of you have done Euclidean mathematics. For the sake of being very correct and very complete, I wanted to put that in there. A linear transformation of the rotation spinning something can be through an angle theta. So I'm going to spin it 90 degrees or whatever. That is represented mathematically using this matrix. It transforms X and Y coordinates and rotates them. Oops. Do you see now why we used that form on the previous slide? This. I wanted this form, and in order to do that, If I organize it this way, I get that. Hey, that's really nice. And that's, oh, somebody said screenshot, so I'll hold for a second. Okay, remember, this is on YouTube, so if you miss it, you can always find it again and you can pause it and frame it on your, please don't do that, but you can. I can't stop you, you're allowed. Okay. This is why we did this way, because it gives us this nice, friendly, recognizable form. You can write it any way you like. This is convenient. And some very smart people said, well, isn't it more convenient to think of it this way? And they're right, it is, because it looks like something we know from elsewhere. So let's use it. Somebody else made us a tool. Don't reinvent the wheel, use it. That's why we wrote it in that crazy way with the colors and the highlights, because it's convenient for the next step. Okay, so I put the rotation matrix up in the corner again, just so you don't forget. Remember, okay, let's go back to the big picture. Rover's algorithm, we said that this is going to use phase rotation, but another way to think about phases is just angles, right? Like theta. Do you see the connection here? We said, oh, we're going to do matrix, we're going to find unsorted search by using phase iterations, phase rotations. Okay, but you can't have a rotation without an angle. Okay. Here it is again. That is our G matrix. Actually, it's G squared. Should have written that. G squared. We can just read it off, can't we? Isn't that nice? That's why we wrote it this way, because it makes it so easy to just read it. It's so nice to read this. I don't want to read that other thing. God, that looked terrible. This is sexy. Now, Erica, what is the connection between psi and this H thing? Right? Remember, these are at the beginning. Before we apply G, everything was just an equal superposition, which is like this, okay? Couldn't we just write it like this too, because of this? Do you see it? This is really, really, really important. We took this, okay? So we said sine theta is equal to a over n root. Do you see how that all works? It's kind of magic. Because this coefficient, we are explicitly told it's right here. If this doesn't make sense to you, that's okay. Go through it again, take a nap, go through it again later, maybe next week. Sometimes things need time to sink in, and there's nothing wrong with that. That's how people learn. It's through repetition, not through once and done. Okay. Cool, huh? That's pretty magical. Somebody earlier, here, I'll leave this up for a minute to let everybody peruse. Right before my talk, somebody asked me, what inspired you to go into this field? It's stuff like this. This was not on my first day. Absolutely not. But this is why I kept coming back. Stuff like this, because there's like a fundamental magic happening here. It's just math, but something cool is happening. And we can find these little connections. And I think that is the coolest thing ever, because it's just math, isn't it? And it corresponds to reality. Reality doesn't have to listen to math. Why should the universe follow math? And it does. To me, that is nothing short of magic. Okay. So what happens after k iterations? Because remember, we don't just apply this G thing once, we apply it several times. Well, let's look at that. Now remember, this matrix, come on. Ugh, I should have written this. This thing was that thing squared. So every application of G is 2 rotations of theta. I'm going to say that again. Every application of G is equal to 2 rotations of theta. Okay? That's actually going to be easier to see in the picture that I have coming up. Okay? Remember, we start with one of them. We get one for free because that's the initial state, wherever it is. And then every subsequent, we get 2 copies. So after K applications, this is going to be the state. Somebody said, how cool are so the results are this in the intersection of sine and cosine? Sorry for the caps. Don't be sorry. It's exciting. Given this equation, what was our overall goal? Remember, big picture. I'm trying to keep track of that. I know we're in the weeds and there's lots of detail in circuses and fireworks, and there's probably a dog barking somewhere. What was the big picture? We want the good strings. We want some result at the end to come from that good string set. I don't care which one it is, whether it's one answer or one of many. I don't care. I just want a good answer. That's all I want. So I'm just going to let you guys read that. Notice this is also a tiny bit backwards. I put sine A, so A is the good stuff. This is on purpose. And you might say, Erica, why did you do that? Stop doing the backwards alphabetization thing. No, it's on purpose. The reason is because we typically prefer cosine to come first. Some of you may remember this from Euler's formula, KISS form, cosine I sine. We just like to put cosine first. But cosine is associated with the bad strings because of the way the rotation matrix works. So this is on purpose. This is not a typo. But remember, we want to maximize this, the chance of getting something here. So that means we need to maximize this probability and minimize this one. Do you see? Maximize this so that this is minimized. So we want this to approach 1. If we could, we'd love it to be identically equal to 1 because that means we are guaranteed a right answer. But it's reality, and reality doesn't care about what you want. Reality says you can do pretty good. So we want it to get as close to 1 as we can. Maybe 99% is good enough. So how many iterations of K do we need? We have at last arrived. How many times do we need to do K? Well, let's find out. This is what we want, right? Because this will maximize the probability of getting a good string. That is to say, go back to your depending on what age you were when you took trigonometry. This is what we want. Pi over 2, for those that may be a little rusty, that's 90 degrees, okay? We want this to approach pi over 2 or 90 degrees, okay? Interesting sidebar. I didn't realize this, but like, I'm in the science world. I think exclusively in radians. To me, that's natural. And I once was asking my husband, I was like, why would anyone ever use degrees? Degrees are dumb. And he said, well, I'm an engineer and I use them all the time. Oh, well, that makes sense. When you're building a bridge, don't you want the bridge to be in degrees? What is a radian when you're building bridges? Ugh. Just an interesting perspective I didn't have. Just little sidebar. Anyway, sometimes it's nice to have commercial breaks when we're learning hard stuff, right? Okay, back to the show. 2k plus 1 theta, we want that to approach pi over 2 or 90 degrees. So your pre-algebra days say isolate the variable, right? So let's isolate k, and we get this. Okay. All right. So we have this, right? Remember this nonsense? This is how we got sine theta. Therefore, isolate theta. This is from that rotation matrix like 2 slides ago, okay? So this is true. Nothing too crazy here. This is still just trig 101. Now, some of you may be familiar from your physics classes that when the argument of sine, like the bit inside, is small enough, you can kind of sort of say that it's the argument value itself. Like sine theta, if theta is super tiny, you can just say it's equal to theta. That's an okay approximation to make. If n is large enough, we can just do that. And you might say, Erica, what if n isn't large enough? Okay, but if n isn't large enough, then why are you doing an unsorted search in the first place? If there's only 8 options to search through, you don't need this algorithm. I got news for you. Just do that. But if n is like 500 options, well, 1 over 500 is pretty darn tiny, especially when it's the root of it, isn't it? So then this is legal, okay? Therefore, we have this value for theta. Let's take that value for theta. And just like your algebra days, plug it in here. And someone's jumping the gun. Yes. We're getting there to the scaling. This is a lower bound, which is not the same as scaling. A lower bound means that at minimum, it has to take this long or this many steps. But this also serves us to show that it scales as big O notation root of n, which is so much better than the linear search, which is what a classical computer would have to do if there's no sorting. Okay, so this is how many iterations of k. K is dependent on how many options you have. So if you have 50 options, k is going to be one number. If you have 4,000 options, k is going to be a different number of iterations. Okay, that's not so bad. And we can calculate that. So you can figure out what is the optimal number of k, because remember, if we overshoot that, your results start to degrade and you start to get garbage. Nobody likes garbage. Here is a visual representation. And I promise we're almost done. I know some of you are like, oh my God, this has gone an hour too long. What the hell? I get it. I'm sorry. We are almost done. Here's a picture. When we start, psi is here. Now you might say, wow, it's closer to what is this? Well, remember that psi is a sum of good and bad, right? So we're going to say that the bad angle or the bad axis is here, okay? And the good stuff is stored here along what is considered the y-axis, okay? And at the beginning, it's in superposition. So if you think about it, remember your right triangle trig days? Remember those good days when life was so hard? A squared plus b squared equals c squared. This is c squared, right? This is the state. This vector here, along the horizontal component, corresponds to the bad strings. The vertical component corresponds to the good strings. And when you square them and sum them, you get the full probability, which is all answers. Oh, stop that. How dare. I don't know what just happened. Okay. So this is where we're starting. I don't know what the right answer is, but at the beginning, psi could be anywhere in this arc, in this first quadrant. I just picked something at random. Don't read into it too much, okay? It doesn't have to be in the middle. Why? Because if there are more bad answers than good, well, then that component of the vector is going to be larger, isn't it? This leg of the right triangle is going to be bigger because there are more bad answers than good. That's just how that works, okay? Don't get too hung up on that if I'm speaking gibberish to you. It's just if you like thinking in terms of circles and trigonometry, this is for you. Okay. So what's the first thing that we do? We're going to start by using an oracle that uses PKB to flip it. Okay. The bad solution axis just happens to be coincident with the x-axis. Okay. Nothing too crazy here. These angles are the same. They might not look like it, but I was freehanding this. So strictly speaking, this angle and this angle, all I did was reflect it. That's it. Just a reflection. Now what? Remember we said it's a double rotation. We rotate twice. Remember that? We're going to rotate through the same angle. What happens when I take this and multiply it by 2 and rotate back in the positive direction, the counterclockwise direction? I end up here. You notice how it's getting closer to the y-axis, which we said was the good axis. Those are where the good strings are hiding. Notice also, if I complete the right triangle using the origin and drop a perpendicular, notice now that the vertical component is larger than the horizontal component. That's kind of what we want, isn't it? our probability of getting the right leg of the triangle is better. If I show another version of this where you reflect across the x-axis and then you reflect it back up, you would see it get even closer, and this picture would be so cluttered you couldn't see it. So I didn't do that. But you reflect over the x-axis and then you do 2 rotations, 2 theta. And you do that k times, and you get really close to the y-axis, which was to be shown. Okay? By the way, for any of you that have this book, this is by Michael Nielsen and Isaac Chong. And of course, the title is not showing up. This is Quantum Computation and Quantum Information. This is like one of the Bibles of the field, right? This is how they describe it in the book. I actually kind of copied their picture a little bit with some modifications. So you can actually go read about this if this like didn't work for you. There's a whole explanation there. Cool. That's it. We're done. Let's have a few minutes for discussion, and then we'll call it a night or an afternoon or a morning, depending on where you are in the world. Okay? Give each other a high five if you're sitting with a friend. You did it. You got through Grover's algorithm, all 4 versions of it. The first thing we want to talk about is complexity theory. This says, how many operations do we have to do to execute a full algorithm? We have the following conclusions. We've kind of said this several times. Here it is summarized. Okay. For classical computation, it scales linearly. That's linear search, because it's kind of random and kind of a mess. The lower bound, which is given by omega, which is not the same as big O. This is saying the lower bound, this is the minimum number of times we have to do something. Where big O is the scaling, this is the minimum number of times we have to do it. And you could say, wait, I sorted the data first. Okay, good for you. And that's a good step, but it doesn't fix the problem because, okay, great. You just spent all that time sorting, which is an n log n operation, and that takes forever. So first you have that, and then on top of that, you have to use a classical search algorithm. So great, you did a lot of work, and sometimes that's the right decision. I am not hating on that. That is the right play. But if you have a quantum computer, why not just cheat? Thank you, Grover. Because this is much faster. Yay. Some final thoughts. You didn't understand. That's okay. You literally got shown this in 2.5 hours at the end of a week of lectures. It's okay. Congratulations, you are normal. Okay. We superpositions and phases, like what the heck is all of that? That's okay. Maybe my learning style was not helpful for you. There are so many other resources. Gibran has lectures. You have your Jupyter notebooks that you can go through. There's stuff in textbooks all over the place. Tons of resources. Okay? Find one that works for you. I will not be offended. You only understood half of it. That's also normal. Some things just make sense to some people and some things make sense to others. That's why we went through all of it, so that you can pick and play. It's all the same stuff, but if you understand half of it, maybe the other half will come faster. Just, you know, they don't ask you how you got to the finish line, provided you got there, right? Do I have any advice for learning this stuff better? Yeah, matrix algebra. Matrix algebra is the key. If you can understand matrix algebra, you're in much better shape. Okay. Linear algebra is the field of mathematics. I also think that of all the things I said, hey, you should try this on your own. Okay, you can do all of that, but this is the one that I want to draw attention to. For your first week as a quantum mechanics student, try out PKB on your own. Work through the math. Do it yourself. It should not take you hours and hours and hours, but it is very powerful. It is definitely a quantum mechanical effect, which means you don't have to work too hard to see quantum mechanics in action. And it's kind of powerful and it's all over the place. So it's a good one to have in your pocket. Oh my God, this algorithm was fantastic. Why are we not using it? Oh my God. Well, I agree. It is pretty awesome. What do you guys think? Why can't we use this today? My brain is not braining. Yes, it is a quadratic speed. How many qubits do we need for a practical application? Well, how many things do you want to encode? Remember the string, if you only have 3 qubits, the biggest you can go is 8. If you have 5 qubits, the biggest you can go is 32 objects. Do you see the problem? Computational power, that's part of it. Error correction is a big part of it. How about this? Qubits aren't coherent. They don't stay coherent very long, which means that by the time I load all my data, the coherence is lost. I don't have enough time to feed everything in. There just isn't enough time because it only lasts for a few milliseconds. What if I have to load a database of 1,000 objects? Remember, there's this trade-off. If it's small enough that I, as a human, can sort through it, then I don't need a quantum computer. If it's big enough that I, as a human, cannot do it or don't want to, then my quantum computer has to load all of that data. It's an I/O problem. Because the quantum computers are not stable enough yet. They're working on it. That's part of what we saw this morning in Dr. Oliver's group. They're working on it. And with that, thank you. I know it has been a very long day at the end of a very long week. I know that. So without further ado, I'm going to stop here. I am so sorry for taking an extra hour of your life. Find me on Discord if you have questions or comments. I will stick around for questions now, but if you have to split, thank you for joining me.
Thank you so much, Erica. I think everyone is really grateful that you took 1 more hour of their lives. Wow, I see so many positive comments on Discord. I see many positive comments in further chats. Astro Yara from USA and Brazil says, thank you so much. You're an amazing teacher. Hannah from India says, thank you. It was really, really helpful. Sarana, thanks, Erica. Very nice presentation. Maya from Iran says it was very informative and interesting. Thanks a lot, Erica. I also heard from the team that you were such an engaging presenter and lecturer. So, wow.
What a compliment. Thank you all for everyone. I see the flood on Discord. You guys.
Yeah.
Thank you. Oh no, my coffee is not cold. Thermal
lecture?
insulation.
Erica's coffee is cold like helium-4. Great, 4.2 Kelvin. Fantastic. It is late for everyone, so if there are further questions, please ask them in the QBronze channel. With this, you should be ready to dive further in all exercises, quizzes of QBronze, including the last one. Maybe not now. I can imagine many brains are pretty fried right now.
Mine too.
Yeah, Ryan from Bangladesh asks, how am I even supposed to sleep? I am sure you will have very interesting quantum dreams. Again, Erica, thank you so much for this great lecture, and we are always open to host you again. Wow, everyone, big respect. You stayed on until, well, 1 hour after the final time. Did so much today. The keynote by Bill Oliver, the virtual lab tour, everyone's so engaged. Now this whole lecture on Grover's algorithm. Vikramaditya from India says, I finally understood Grover's search in more depth. That is amazing to hear. Petition to host Dr. Erica again. Okay, I have good news. Erica will definitely back with a presentation on her project, the Womanium Quantum Solutions Launchpad project, which she is doing with the Naval Nuclear Lab, working on DFT simulations on nitrogen vacancy centers in Diamond. So stay tuned for that. And thank you for sharing all of this. I would like to give a preview of what we are going to do on Monday. That will be a really important day. We will look more into the hardware. What are quantum computers actually? How does it work with superconducting qubits? How does it work with trapped ions? Why? How are they used as qubits? How do you then build a quantum computer out of it? This will be a more conceptual, intuitive lecture, less maths and derivations. 1 hour on the basics of quantum hardware, superconducting trapped ion, neutral atoms for your understanding. And then we will start a week of quantum annealing, a different concept on which we will learn first about the basics and hardware. And then on Wednesday and Friday, we will do more implementation. There will be a demo by D-Wave. There will be a module, Cobalt, by QWorld. So this will be a very exciting week, and also very useful for applications that we will dive in further later this program. Okay. I hear now I have to use Grover to find my brain. I feel you. Let's stop for now. We stayed for a long time. Amazing, you're all here, have been stayed until the end, and I really look forward to seeing you all again next week. Monday, quantum hardware, then quantum annealing, then all the upcoming weeks, advanced quantum algorithms, quantum machine learning, projects coming up. Stay in touch on Discord, and keep sharing more also about your world in the Share Your World channel. It is lovely to see, and thank you all. I look forward. Next week we will probably host a happy hour where you can share flash talks about the things you are doing. Maybe you are already doing research or you are learning certain things, so you can give a 3-minute flash talk on that. And then we will do a happy hour to get to know each other more beyond Discord names and some faces here. Some people turn on their cameras. That is really great. Only the hosts can see you. But for me, it's always wonderful to see the faces belonging to the names. And then from next week, hope to get to know each other better in the happy hours. The time and day of the happy hour will be announced further. Okay, thank you so much all. Have a great weekend and a great night, afternoon, day for now. And I hope that your fried brains can recover soon, and we will have a great kickoff of the week 2 of the program from Monday. Thank you.